So our remaining functional groups that we're going to look at will all show up in sort of the 1600 to 1850 range. And all of these are sp2 carbons. So we're going to start here with alkenes. Alkenes are generally in a range of 1620 to about 1680 and are usually medium intensity. And we can see an example of one here. So the other functional group that shows up in this region, or a similar region at least, are carbonyls. And the most common way that we can differentiate between carbonyls and alkenes is the strength of the peak. So this alkene that I have shown you here, 1-hexene, is fairly strong as far as alkenes go. Most alkenes, though, are a bit weaker. Carbonyls, on the other hand, are generally fairly strong, as we can see by this spectrum here. So here we have a ketone. Ketones generally start in the range of 1710 to 1725. Now, it's especially important to note, especially now that we're dealing with carbonyls, that these ranges are a starting point. We can still have ketones that show up above 1725. We can have ketones that show up below 1710. And later on, we will discuss some of the things that can push us to higher or lower wave numbers. But this is our starting point, and it's the range where the majority of that functional group is going to fall. Aldehydes show up in a very similar range. Slightly higher, 1720 to 1740, but a pretty similar range to ketones. And again, we can see that it's a very, very strong peak for the carbonyl. But aldehydes and ketones can be easily distinguished because having a hydrogen directly attached to a carbonyl, which we find in an aldehyde, also gives us two peaks between 2700 and 2900. And that actually makes aldehydes one of the easiest functional groups to pick out in an IR spectrum, because this 27 to 2900 range, there's almost nothing else that shows up around there. And it's just about always two peaks. So anytime we see this combination of the carbonyl peak and the two peaks from 27 to 2900, we can be pretty certain that we've got an aldehyde. Here we have an example of an ester. Ester is slightly higher, about 1730 to 1750. And then finally we can look at an amide. An amide, because we've put a nitrogen on there, actually shows up at slightly lower wave numbers. In fact, it overlaps almost completely with the alkene, 1630 to 1680. There's two main differences, though, between the alkene and the amide peak. One is the amide, being a carbonyl, is generally strong, whereas the alkene peak is, sort of medium in intensity. But also, and we can see that here, many amines, but not all amines, many of them will give us two peaks. So now we've started to get an idea of the types of peaks that we see, where those peaks show up. And after this, we'll start looking at some actual spectra. Before we do that, though, a couple points I want to re-emphasize. One is that, again, IR is good for determining functional groups. So here we have two molecules that are very, very similar. They're 3 carbon chains with oxygens attached to the middle carbon. The difference, though, one of them is an alcohol, one of them is a carbonyl. And it turns out that makes them pretty easy to distinguish. We have the large peak up here, in the mid 3000s for the alcohol, versus the peak here down around 1700 for the ketone. And so we can easily distinguish between those two compounds. But we can also see that IR is not great for telling us anything about connectivity. So these two molecules are isomers of each other. They are both C3H8O. They're both alcohols. The only thing that's changed is whether the alcohol is on the first carbon or on the second carbon. And in terms of the functional group, they're both strong, broad peaks for the alcohol. Now, I think this is the most remarkable piece here. Remember our fingerprint region that we talked about earlier? That's this part of the spectrum. By just moving that alcohol group over 1 carbon, we can see just how much that changes the fingerprint region. The alcohol is pretty much the same, but the fingerprint region is drastically different. Now, another thing that you'll find once you get into the lab and you're taking your own IR spectra is that before you can take a spectrum, you have to take what's called a background spectrum. And that's where you'll use that metal plate that you saw in the picture, and you'll run the spectrum, and it'll prompt you for it with nothing on the plate. The reason we have to do that is even things that are in the air, such as carbon dioxide and water, they give us peaks as well. And so what happens is that we take what's called a background spectrum, and then the software automatically subtracts that background out of your spectrum. That way you don't see the water peak or the carbon dioxide peak or anything else that might be present in the air. Now, we did also note earlier that there are certain things that can affect where a peak shows, that these ranges that we talked about are really just starting points, and that not every compound we look at, every spectrum we look at, is going to fall within those ranges. So are there things that will determine whether something can fall at a higher or lower shift? And the answer is yes. The main determining factor is, do we have an electron donating group or an electron withdrawing group? So there are other factors that can come into play, but this is the most important one. Let's look at how this works. So if we have this compound, just a 6-membered ring containing a ketone, we find that the IR spectrum here gives us a shift for the ketone of 1715. Then we change the compound slightly by adding an alkene. As a result, we find that the carbonyl peak shifts all the way down to 1685 wave numbers. So we can see by adding that double bond near the carbonyl, we get a fairly significant difference in the IR peak. Why do we think that is? Well, what can we draw for resonance structures for these molecules? So as we learned back in the first chapter we covered in this course, for any carbonyl, we can always draw a resonance structure where we shift the pi electrons up onto oxygen and we get the plus and minus charges. And we can do that for both of these ketones. But what happens in this second one? Well, after we form this resonance structure, we have an alkene next to a positive charge. So we can draw a second resonance structure. That looks like that. Now, is this enough to explain the difference in where the peak shows up? It turns out that it is. So when we have this extra resonance structure, this is an extra resonance structure where the carbon-oxygen bond is a single bond. So that means resonance structures where the carbonyl is shown as a single bond are more important because we've got two of them here compared to just one for the first molecule. So what that suggests to us is that this compound, the second one, has more single bond character. It's not actually a single bond. Because a carbon-carbon single bond has IR shifts that are hundreds of wave numbers lower. But it has a little bit more single bond character. What that means in turn is that it's a weaker bond. Because it's a weaker bond, it shows up at lower wave numbers. Therefore, the 1685 versus the 1715. So in general, if we have an electron donating group, and what we're going to talk about here is, or summarize here, is mostly relevant to carbonyls. That's the biggest place where we see this, but it can apply elsewhere. Electron donating groups, by giving us more single bond character in a carbonyl, lower the delta E, which takes us to lower wave numbers. If we have an electron withdrawing group, though, that usually results in a stronger bond. Well, we know a stronger bond, higher force constant, requires a higher energy, and higher energy leads to higher wave numbers. All right. Now you may have noticed there are some other functional groups that we haven't talked about. Some functional groups that we learned, but we haven't really gotten into their IR spectra. And there's reasons for that. The reasons are that they fall into ranges that aren't very useful for us. So for example, the carbon-nitrogen single bond shows up around 1250 wave numbers. We also didn't talk about ethers because a carbon-oxygen bond shows up, around 1300 wave numbers. And so both of those are peaks that we don't really see very well because they're in the fingerprint region. We also didn't talk about thiols, and that's because the SH bond is in about this 25 to 2600 range, but it's very, very weak, and so we can actually barely see it. All right, so from here, what I want to do now is I've got some more spectra. Basically, the question is, what functional groups do we see? Because that's to a large part how we treat IR. So here's our first spectrum. Take a look at this for a minute or two and see what you come up with. All right, so what did we find? Well, the first peak I see here is this very, very strong peak. And to me, that looks like a carbonyl peak. Now, it's at about 1710. It's just over 1700. So my initial thoughts would be that it's a ketone. We know it's not an aldehyde, because if it was an aldehyde, we'd see those two peaks around 2800, and those clearly aren't there. But we do definitely see the carbonyl peak. And then next to it, just above 1600, it's a weaker peak, more medium intensity. Looks like an alkene. So let's look at the actual structure. And we can see that, yes, it does definitely have an alkene, so we were right about that. But the carbonyl peak, which is showing up at 1717, ends up being an ester. And that's definitely lower than the range that we talked about for esters previously. So why is it that it's still an ester, even though it's lower than we would expect? Well, it's the same thing we just talked about a few minutes ago with the resonance. We have an alkene here as well as an aromatic ring that are both conjugated to the carbon of the carbonyl. That's going to push it to a lower range than we would normally expect to find it at. All right, our next spectrum should be pretty straightforward. There's our big alcohol peak, and this is methanol. All right, now take a moment and try this one. So the first thing we probably notice is that we have an alcohol, because we have this, our strong broad peak there. But if you notice, the shape here down at the bottom is a little bit funny. Normally, and I know we haven't seen a lot of spectra at this point, but normally the bottom of an alcohol peak is fairly straightforward like that. And this one's kind of pointed like that. We also see an alkyne here. So those are the two major functional groups that we see. We have an alkyne, we have an alcohol. But when we look at the actual structure of the compound, we start to get a hint as to why that peak is so oddly shaped. So the alkyne that we have in this molecule, we can see here, is terminal. And remember, a terminal alkyne is generally going to have a peak around 3300 wave numbers. And so if you think about what's going on here, if we have our alcohol the way it would normally be, and then if we also had the CH of an alkyne, and those two peaks are just sitting on top of each other, with the CH just kind of peeking out a little bit at the bottom, that would explain the weird shape that we're getting here. And we've got one more here, and I think in this spectrum we can make out the carbonyl here and the alkene here. So from here you've got some practice problems to work on that deal with identifying functional groups in infrared spectra. So go ahead and work on those, and we'll go over them next.